So earlier in the course we've seen how, given information about a derivative, you can find out information about the original function. For example, there was a problem on the exam where you were given the graph of the derivative and you had to sketch the graph of the original function. So this process of going from the derivative back to the original function is called antidifferentiation. So the definition is that we say g of x is an antiderivative of f of x if the derivative of g of x is equal to f of x. So in other words, f of x is equal to g prime of x. So if we're given g prime, we want to find g. So it's like doing derivatives in reverse. So as an example, if f of x is equal to x to the power 4, then the antiderivative is 1/5 x to the power 5. Why is this? Because when we differentiate this function, the 5 would come down and cancel the 1/5, and we just get x to the 4th. So the derivative of this function is equal to x to the 4th. But I really should say an antiderivative of x to the 4th is equal to this, because there's more than one. For example, I could take 1/5 x to the 5th again, but then add on 1. If I take the derivative of this constant, it's 0, so it still doesn't change the fact that the derivative of this function is x to the 4th. And of course, I could add any other constant I want here, like plus 2 or plus 7 pi, and since the derivative of a constant is always 0, it wouldn't matter. So in general, I could have the antiderivative to be 1/5 x to the power 5 plus c, where c is just some constant. So it could be any of these numbers or something else, because the point is the derivative of the constant will always give 0, and we get back to x to the power 4. So this means that the antiderivatives form an entire family of functions. So this is, roughly speaking, what 1/5 x to the 5th would look like. But then there's all these other possible antiderivatives as well, which just involve shifting the function up or down. And so as you can see, by just shifting the graph up or down, the slopes of the tangent lines don't change, so the derivatives do not change. And that is why all of these are antiderivatives of the same function. Well, the way I've drawn it, this one looks a bit steeper, but it should have the same sort of slopes as the rest. Okay, so here we did the antiderivative of x to the 4th, and the way I came up with this was basically just using the power rule in reverse, because I knew that when I differentiate something with x to the 5th, I would get something with a power 4, and then I just put this 1/5 out front so that the constant that comes down would cancel out when I use the power rule. So there's a general formula that sort of represents how this works. So it's the power rule for antidifferentiation. And it says that the antiderivative of x to the power p is equal to 1/p plus 1, x to the p plus 1, plus a constant. And this is for p not equal to -1. So by the way, this symbol I've drawn here, as well as this dx that I wrote here, so these things, these are all just part of the notation for an antiderivative. So this expression on the left is just saying the antiderivative of x to the power p. And it's given by this formula. So for example, if p is equal to 4, then we would get from this formula exactly what I claimed the antiderivative to be up here. So why is p equal -1 bad? Well, you can see that in that case we'd be dividing by 0. So of course we cannot do that. But in fact, we know that if p equals -1, the function we have is really 1 over x. And we know that the derivative of natural log of x is equal to 1 over x. So in fact, this rule doesn't apply, but we can figure out what the antiderivative when p is equal to -1. So the antiderivative of x to the -1 power is going to be equal to natural log absolute value of x plus a constant. So you might be wondering, why did this absolute value of x appear here? Well, without going into too much details on this, x to the -1 power is defined everywhere except for x equals 0, right? It's just 1 over x. Log of x, though, recall, is only defined if x is greater than 0. So if we want something to be the antiderivative of x to the -1, it should be defined for negative x values as well. So it turns out that putting this absolute value on here makes it so that that works out. Basically, you pick up a negative sign because absolute value of x becomes negative x if x is a negative number. And then when you take the derivative by the chain rule, you just get a negative out front, but you still get the 1 over x. But then, of course, since x is negative, it agrees. So I realize that was very vague, but the point is it is important to have these absolute value signs on here in order for this antiderivative to work for negative x values. Okay. So that's the antiderivatives of power functions, but you can also find antiderivatives of lots of other functions by just using the rules that we've learned throughout the class in reverse. So for example, the antiderivative of sine of x, negative cosine of x. This is because we know the derivative of cosine of x is negative sine of x. So if we put a negative sign out front and take the derivative, then what we get is exactly sine of x. Similarly, we can have that the antiderivative of cosine of x, sorry, there should have been a plus c there, of course. It's very easy to forget plus c's, so make sure to be careful about that. Antiderivative of cosine of x is equal to sine of x plus c, because we know the derivative of sine is cosine. Similarly, you can have things like antiderivative of e to the x is equal to e to the x plus c from the rule for the derivative of the exponential function. And if you recognize some inverse trig derivatives, then you should realize that the square root 1 minus antiderivative of 1 over square root 1 minus x squared gives us arcsine plus c, and similarly the antiderivative of 1 over 1 plus x squared is equal to arctan plus c. So basically all these come from just taking the rules that we already knew, writing them in the reverse direction, and then adding some plus c's because you can always add a constant to the antiderivative. So let's see an example. So let's suppose f prime of x is equal to 2x to the 7th minus 4 cosine of x. And we're given the further information that f of 0 is equal to 1. And we want to find the original function f of x. So we want to find the antiderivative of this function. We have two pieces to it, the 2x to the 7th and the 4 cosine x. So 2x to the 7th, we'll want to use the inverse power rule that we were just looking at with p equals 7. So in that case, we get 2 divided by 8 times x to the 8th minus, now for this one we have to find the antiderivative of cosine. We set up here that that was sine. So we have 4 sine of x and then plus a constant. Now we're given the information that f of 0 is equal to 0. So if this is our, to 1. So if this is our formula for f of x, it should be true that when we plug in x equals 0, this will give us 1. Well, what happens when we plug in x equals 0? Well, we get x to the 8th becomes 0, and sine of 0 is also 0, so we just get f of 0 is equal to c. This means that given this additional information, we can actually get rid of this unknown constant and determine that c has to be equal to 1. So f of x, finally, is equal to 1/4 x to the 8th minus 4 sine of x plus 1. So usually there's a whole family of antiderivatives because you can shift by a constant, but if you're told one value of the function, then suddenly you know exactly what the value of c is and you get a unique antiderivative. Okay, so these are sort of the basic antiderivatives that you should, I think, be able to recognize on sight, some combinations of all these things in the power rule. But there are some more complicated ones. So you learn more systematically how to do this sort of thing in Math 112, so I'm not going to spend too much time on it here. But just as an example of other sorts of antiderivatives that maybe you can recognize, if we want to find something like antiderivative of x to the 4th sine of x plus 1/5 x to the 5th cosine of x dx, then here you notice that we have one term plus another term, and they're related in a very specific way. If I call this f of x and this g of x, then this is suddenly g prime of x, and this is f prime of x. So if you realize that it has this pattern, then you can see this is the antiderivative of something like f prime of x times g of x plus f of x times g prime of x. That should remind you of the product rule for derivatives. So if we want to know how did we end up at something like this, what function do we take the derivative of, we can use the product rule in reverse and get that this should be equal to sine 1/5 x to the 5th sine of x plus a constant. And you can check, if you apply the product rule to this function, you will end up with this thing that we were trying to take the antiderivative of. So spotting something like this can sometimes be much more difficult than some of these more elementary combinations of functions. But I think it's worth trying to do this if you see something more complicated. I think it's fine if you have some difficulty seeing this quickly, because really it's just based on whether you spot the pattern or not. And in this class we're not going to learn any more systematic way to do this, even though there are methods that would let you arrive at this answer more algorithmically. Okay, so that's a quick introduction to how to find antiderivatives. A couple quick remarks that maybe can be useful. One is if you're doing an antiderivative problem and you get an answer and you're not 100% sure about it, you can always take the derivative of the answer you got and check to make sure that your answer actually works. So this is convenient because taking derivatives, we've been studying it for a while. It's something that hopefully you're comfortable with doing. And so you can say it's on an exam and I ask you to find an antiderivative. You can immediately know if your answer is correct or not by taking the derivative of your answer and checking to make sure that it matches the function you were anti-differentiating. So that's quite useful. The other warning I want to give, I already gave it earlier, but I'm going to give it again. This plus c, it's very important, it's vital in order for your answer to be correct, but it is extremely easy to forget this thing. So please, when you're doing anti-differentiation problems, always take a moment at the end and go back and check to make sure that you always have a plus c where you need it. Okay, so we'll come back to antiderivatives later in the class, but I want to say about this for now.